Hello, and today we're going to be talking about geometric series again, but this time we're going to be talking about an infinite sum. So first I would like to take a look at the formula. In particular this version of the formula. Okay, so we want to work out what this series to an infinite degree is. So if we plug this in, that means we're taking something to an infinite power and then we're gonna... that doesn't make a whole lot of sense, does it? It could make sense if modulus r was less than 1. What happens if we have something less than 1, for example, a half, and we took it to some power? It gets smaller. So if we took this to some sort of infinite power, it should get infinitely small. So we should get something that's less than 1 to an infinite power, modulus r, such that it fills this requirement to an infinite power. It should turn into nothing. It should get infinitely small to such a degree where it's gone. So if we think about that, we get what's something called a converging series. So if we were to graph when modulus r is less than 1, we get something that kind of starts high and then gets really, really small as time progresses. Right, here's our graph, and it keeps going smaller and smaller. In comparison, if modulus r is greater than 1, we're going to get quite the opposite. We're going to get something that gets bigger and bigger and bigger. So we call this converging because it's heading towards a certain point, and here we're saying diverging because it never stops. So back to our original problem, we want an infinite sum. If modulus r is less than 1, that means r in here becomes 0. So let's sub that in. Well, 1 minus 0, that's just 1. And 1 lot of a, that's just a. And there you have it. You have an infinite sum for a geometric series. Please note that there's an infinite symbol. And please note the position of r in this equation. We don't want r minus 1 divided by a, no. You want 1 minus r. So now we're going to do an example. If I had 1 plus a half, plus a quarter, plus an eighth, so on, how can I sum this all together? Well, we can use our infinite sum again. So our first term 1, and our common rate, a half, minus 1, is going to equal 1 divided by 1 half. That equals 2. So what we've done is found a finite amount for an infinite sum, yet this infinite sum can never reach this finite amount because there's always that little extra bit. Okay, let's look at a different application. I would like to bring your attention back to a reoccurring decimal like we have here. So what this is really 2, 1, 2, 1, dot, dot, dot. And we want to represent this as a fraction. In the previous video, we did that, but we can actually work out a fraction using an infinite sum. What we do is we set our a value to equal 0.21, what we want to repeat, divided by 1 minus, and the rate is going to be 0.01. Now, why is that? If we put this into a geometric sequence, here's our first term, here's our second term, here's our third term, and this will keep going. And all we're doing here is we're infinitely adding it. So if we were to try and solve this, you'll get 0.21 divided by 0.99, and then we can times by 100 over 100, which is still 1, and we get 21 over 99. You can check that on the calculator, and that will equal our reoccurring decimal here. If you try this with other decimals and try and get it to work, and this first digit here is greater than 5 or equal to 5, you might get your calculator rounding, but that's just it rounding off. Let's do another decimal example. Let's say I want 0.123, for example, right? Recurring. So, infinite series equals our starting term 0.123 divided by 1 minus our rate. In this case, it's going to be 001. The amount of zeros, right, including where the decimal point is the amount of digits reoccurring, right? If you can remember that, you should be able to get the hang of this. Alright, let's work out what that is. That's 0.123 divided by 0.999 times that by 1000 over 1000, and we get 123 divided by 999. We can simplify down, so it should be 41. So 41 divided by 333 does give us our reoccurring decimal. What if we have something like 0.2111, and this is recurring but not the 2? We can apply the same logic but do it slightly differently. So our a value is 0.1, that's what's reoccurring, divided by 1 minus 0.1, right? So if we times these, our first value by our rate, we should get 0.001, and then we can use that as a series. So we get 0.01 divided by 0.9. We will times this fraction by 100 over 100, and we get 1 over 90. That's still not our decimal up here, but all we have to do is add 1/5. So now we can get a common denominator. We get 90 over 450 plus 5 over 450, and we get 95 over 450, and we can divide that by 5. That means that our decimal here is 19 over 90. That's just this simplified down. So that was an infinite geometric series. If you have any questions, feel free to ask in the comment section below, or contact me on social media, and I will try my best to answer them all, and I will see you in the next video.